for being here. It's really exciting to have 30 people all here at the same time. This is just a heads up. We're going to be recording this and putting it on the Talk Math with Your Friends YouTube channel. And unless Sandra feels that she messed up really bad at the end, then it'll go up to YouTube. So, I'm excited because I don't know what a matroid is. So Sandra's going to tell us what is a matroid. Sandra's at Brooklyn College, part of CUNY. And so please join me in welcoming Sandra to Talk Math with Your Friends today.
Thank you. Thank you for giving me this opportunity to give this talk. And I'm really glad to have a whole new group of friends. So I've kept this talk at a fairly elementary level, except at the end, it's a little bit, advanced, but for the most part, it is something that a student who knows linear algebra will get an idea of matroids. So I'm going to begin with what is a graph. It's sort of the easier object than matroids, at least in terms, there's a visual of graphs. It makes it a little bit easier to understand. Then we'll go from graphs to matroids. Then we'll talk about binary matroids and a couple of concepts and a structure theorem if we get to it. So we're beginning from the beginning. This story has a year that it begins in, 1736. So that is an old picture of the city of Königsberg. And the residents noticed that like to take evening walks and crossing each of these 7 bridges over here. And they noticed that they could not cross the 7 bridges and return back to the starting point. Cross the 7 bridges exactly once and return back to the starting point. So that's the question over here. Is there a walk that crosses each of the 7 bridges exactly once and returns to the starting point? So the question again, the leading mathematician of the time, Euler, heard about it. And he was the first person to abstract that real world setup into sort of a map like this with the 7 bridges. And this picture is actually in his paper, which we will see in a couple of slides down. And this picture can be further abstracted to this points and lines drawing. So this is this landmass over here can be considered as this point or vertex C. This landmass can be A. This land over here can be B, and this part D. So now you have a bridge connecting C to D, a bridge connecting D to B, this one connecting D to A, and then 2 bridges connecting A to C and A to B. So now the question is a little bit more abstract from the real world setup. Can you walk along the edges of this figure, crossing each line exactly once and returning to the starting vertex? So what do you think? I mean, I could jump to the end, but do you think it's possible? No. And Euler's idea was that if you have to cross each edge exactly once. And if you enter a vertex, you also have to leave it. And if there are 3 edges touching a vertex or an odd number of edges touching a vertex, then that becomes a problem. So if you enter a vertex, you also have to be able to leave it. So the edges have to be even. So a graph consists of a set of points called vertices and a set of unordered pairs of points called edges. We'll put some terminology to this. So we'll call the vertex set V or V of G to be more precise. And that's the vertices here are A, B, C, D, E, F. And then the edges are unordered pairs of vertices. The idea is to, you can also have directed graphs and then it would be ordered pairs of vertices. So A, B, B, C, etc. So we'll make a definition over here. The degree of a vertex is the number of edges incident to it. So we're building a little bit of terminology and language to express that notion of, you enter a vertex, you also have to leave it. So you have to have an even number of edges touching the vertex. So that would be degree of a vertex. In one more definition, a graph is connected if you can get from every vertex to another vertex. Otherwise, it's like two separate graphs, it's disconnected. So an Eulerian circuit, we named it Eulerian in honor of Euler, he didn't call it that, is a walk along the edges that uses each edge exactly once and returns to the starting vertex. So over here, you can see an Eulerian circuit. A, B, C, D, B, E, D, A. And here, no matter how hard you try, it's a good exercise to give a little kid to keep him or her busy, you will not get it. And then the explanation, one direction is straightforward. After a little time, staring at it for a little bit, you see that if you edge enters, it also has to leave. So it really needs to have even degree vertices. And that's the theorem. Let G be a connected graph. So we have a first theorem in graph theory. And G has an Eulerian circuit if and only if every vertex has even degree. And as, so Euler was the first person who wrote the paper on it, and this is his paper here. But he only proved the easy direction. Like he just kind of waved his hands about the other side. It was 1873 that a young German mathematician by the name of Holzler, who gave the other side. And actually in every graph theory book, this is just called Euler's theorem. It's not called Euler-Holzler theorem. That's just something I put up there. And this figure that we have actually appears in Euler's original paper. So let's ask a slightly different question. Is there a walk along the edges of a graph that uses every vertex exactly once and returns to the starting vertex? So before it was every edge exactly once, now it's every vertex exactly once. So this question was posed by a British rector by the name of Kirtland in 1856. So let's make a little definition over there. A cycle is a walk in which vertices are not repeated. So the question again, is there a cycle that uses every vertex exactly once? Yes, A, B, C, F, E, D. And yes, A, B, C. Did I put that wrong? Is that actually a Eulerian circuit? A, B, C, D. No, there should be no, oh my God, there's a mistake. So you can help me fix it. Does such a cycle exist or not? Let's see, go A, B, C, D. You cannot get back to the starting, right? A, B, C, D, A, but then you're missing E. So real-time question, can we find a cycle that crosses every vertex exactly once? So you're seeing that this is a hard question. So Hamilton followed up on this question and he turned it into a game called the Traveler's Icosian game. So he patented it, and this was he had pegs over here, and the idea was, can you cross every peg exactly once? So that was the analog. And a cycle that uses every vertex is called a Hamiltonian cycle. And that's a famous unsolved problem. Given if and only if condition for the existence of a Hamiltonian cycle, that is unsolved. That is not something that, we know special cases of it, but the main problem is unsolved. It is related to the traveling salesman problem. Consider a graph with numbers attached to each edge. That's called a network, actually, although in the modern use of network is that it's just another word for graph. So suppose a salesman travels to n cities exactly once and returns home. What is the cheapest route? So a brute force algorithm would require n factorial checks. Is there an efficient algorithm? Well, you don't know. This is the traveling salesman problem, one of Clay Institute's $1 million problems. How's it going? Is it clear so far? Okay.
Somebody's wondering if you know the version of Hamilton rewritten to be about this Hamilton rather than Alexander. But other than some silly musical theater, I think we're good in the chat.
And this is William Rowan Hamilton. He British mathematician, not the same. Need just one more concept before we can start matroids. A tree is a graph with no cycles. And this was by Cayley, although the history of math shows that maybe it was 10 years older. It's like nobody gets the proper credit they do in the early history of graph theory here. Correctly, that should have been called Kirtland cycles, but they're called Hamiltonian cycles. So he was looking at saturated hydrocarbons such as methane, ethane, etc. And he wanted to enumerate these things. And he has a nice result on counting number of labeled trees. So that was his motivation. So we need one more concept before we can go to matroids. So let G be a graph with vertex set VG and edge set EG. A graph H is a subgraph. See, just like groups and subgroups, set and subset, graph and subgraph. A graph H is a subgraph of a graph G if the vertex set is a subset of the original vertex set, and the edge set is a subset of the original edge set. So a spanning tree of G is a subgraph that is a tree itself, but the number of vertices is the same as the number of vertices of G. So far, so good? Yes? Okay, so with this much graph theory, we can go on to matroid theory now. So what is a matroid? Let's look at a graph. This is a graph, it's got multiple edges. These two vertices have two edges. And I've labeled the graph as 1, 2, 3, 4, 5, 6, 7. Let E be the set of edges of the graph, and let C be the set of cycles. So 1, 7, 4, 5, 6. This is the full set of cycles of the graph. So we label the edges, and we consider the set of cycles of G. Okay. So Hassler-Whitney in 1935 wrote a paper titled On the Abstract Properties of Linear Dependence. And he observed that the cycles of a graph satisfy the following properties. You can't have a cycle contained in another cycle. That's what the first one is saying. And the second one is saying that if you have an element, a common edge between two cycles, then you can find a third cycle that misses the common edge. So on the next slide, I have the same example again, and then we'll take a look at these two properties again. So that's the example on the previous slide. You have cycles. So take a look at this cycle here, 1, 2, 3, 6, and 4, 5, 6, right? It's got a common edge 6. And if you remove that edge, this is a cycle. So there's a cycle contained in the union minus that common edge. So flagging these two axioms as important was Whitney's genius, as in, you know, graphs was known for a long time, results were obtained, but he observed that that the set of cycles satisfy these two properties. How's it going? So far, so good?
Actually, I have a question.
Yeah.
I'm trying to show a picture up to the screen. I don't know how this works on Zoom.
I'm sorry, say again?
I'm showing something on the screen. I'm holding up a picture to the camera. Here's a picture of a graph. And I've got basically two vertices with four edges between them. Could I regard in my picture as like 1, 2, 3, 4 as a cycle? Now that repeats vertices. And then 2, 3 is a subcycle. I guess part of the definition is the cycle cannot repeat vertices. Am I right?
Yeah.
Okay. Okay.
Yeah.
Otherwise, we'll count examples like that.
Yes.
Okay.
A cycle is doesn't repeat vertices. Yeah. A cycle is a walk along the graph with no vertex repeated.
Okay. So sorry. Be very clear about that. Thank you.
Okay.
So that's why Whitney's paper was titled like linear dependence, right? Because that's, you want like these cycles are like minimal in some sense.
Exactly, exactly. And on the next slide, that independence, dependence will become a little bit more clear. So now consider, so this was Whitney's original paper. He actually spoke about graphs and matrices. So consider a matrix over a field. It can be reals, complex, or in this case, it's the finite fields, F2 in particular. It's a binary matrix, 0, 1 matrix, right? So if we label the sets the set of columns, 1, 2, 3, 4, 5, 6, 7, then the independent sets of columns of A are these. So, you know, a little bit more work to gather up all the independent sets of columns, but here they are. For example, 1, 2, 3 is independent, right? 1, 2, 3, 4 is also independent. But if you look at 1, 2, 3, 4, and 5, that's dependent, because in binary arithmetic, 1 plus 1 is 2, 1 plus 1 is 2, 1 plus 1 is 2, 0, right? 2 is 0, 1 plus 1 is 2. So 1, 2, 3, 4, 5 is dependent. And in fact, this is minimally dependent. 1, 2, 3, 4 is independent. And you can just run through and figure out all the independent sets of columns of A. And by independent, we're talking linear independence, that same concept that you teach linear algebra students, linear independence. So Whitney observed that linearly independent sets of columns of a matrix satisfy two properties. If I2 is an independent set and I1 is contained in it, then I1 is independent. So a subset of a linearly independent set is linearly independent. And that's, again, something that, you know, linear algebra students will know. But the second axiom, it's not that common, and yet the explanation is just a few lines. I do have an explanation for it. So if you do singular value decomposition in your Metroid, in your linear algebra class, then you will see somewhere that you need a result that says if you have a linearly independent set and it's smaller than a basis, then you can grow it to a basis. And that's what this is saying. If you have a linearly independent set I1 less than another one, strictly less, then you can find an element in I2 minus I1 such that I1 union E is independent. So,
Sandra, do the vertical lines there say size?
yes, size, thank you. I seem to have lost myself in this, and you. Let's see, maybe we're lower.
That's okay.
Okay.
So that second one, is there necessarily an E if all we know is that the size of I1 is less than the size of I2? Or are we following it from, I don't know.
That's a good question. Yes, there will be an E, because the idea is that if you have a set of a linearly independent set of vectors in just Rn, and you can add to it to grow it as big as a basis.
Everything's coming from a common vector space. Is that right?
Yes. Yeah. Yeah. So yes. Brian, did I explain?
Yeah,
that?
no, my question was not about the worst case scenarios. My question was actually the sort of the hardest case. If I1 is contained in I2, then that limits the choices you have for E. But if I1 has nothing in common with I2, there's probably lots of them, but apparently the number of them is enough to know that there will at least be one that works.
Yes.
Okay.
Yeah.
Yeah, that makes sense.
And so there's a 5-line explanation for that. Well, suppose I1 union E is dependent for everything, for every E in I2 minus I1. So let S be the span of I1 union I2. Then dimension of S is at least I2, right? It's a span of all the vectors in I1 union I2. So the dimension of S will be at least I2. So span is a set of all linear combinations of vectors in I1 union I2. So by assumption, S is contained in the span of I1, right? Because for every E in I2 minus I1, I1 union E is dependent. So dimension of S is less than or equal to I1, size of I1. So thus we have I2 is less than or equal to dimension of S from here, less than or equal to I1, which is strictly less than I2. So this is a contradiction. That was a good point, Brian. So it's just strictly dependent on the sizes. Any independent set will hold for it. So back to the top. I just scrolled up to make sure I was back in the top and I could see you. Okay. So Whitney observed that the set of cycles of a graph satisfied those two properties, and the matrices, the set of linearly independent columns of matrices satisfied these two properties. And additionally, these are equivalent. So here we have the definition of matroid. Let E be a set and C be a set of subsets of E such that, and those are the two axioms, the axioms on the previous page.
Funny words.
And just got one more, that the empty set is not in C. Then E of C is a matroid, and members of C, just to be confusing, are called circuits. Instead of cycles would have been a better term. When it's called circuits, it has nothing to do with Eulerian circuits. So let E be a set and I be a set of subsets of E such that those two independent set axioms, and a third trivial axiom, the empty set is independent. Then members of I are called independent sets, and that's what matroid is. So Whitney extrapolated these axioms from cycles and from linearly independent sets of columns in a matrix. And what's more, that they are equivalent. And this is just two of about 13 distinct ways of representing, of defining a matroid. So a matroid is like a topological space. It has multiple different definitions, cryptomorphic axiom systems, that's what it's called. You can go from one to the other. And yeah, I think somebody mentioned dependent sets. So in a matrix, the circuits are the minimal dependent sets. And in a graph, the independent sets are just the acyclic subgraphs. And there's also basis axioms, like bases of a matrix. They have axiom, and in like the spanning trees are the bases. So that's what a matroid is.
So so axioms 1 and 3 are the axioms for a simplicial complex. Is that right?
Yes, it's related. It's related to a simplicial complex. Yes, I wouldn't be able to tell you a whole lot more than that, but I go a different direction. But you're right. It's also related to the previous speaker's talk on polytopes. So now a matroid is just a set system, right? It's a set with some axioms associated with it. And Whitney's original paper did not have any, he just had like matrices and graphs. But actually, it's much broader than that. It's, it's basically it's a combinatorial geometry that satisfies certain properties, and that's coming up in a couple of slides. So a lot of my work
Sandra,
has
we
been...
have a question one page back from Andrew. He wanted to make sure that the I1 and the I2 are the right way around. Do you mean in line 1?
Is it?
Yeah, you're saying red axiom 1.
Well, the axioms should be this. If I2 is an independent set and I1 is contained in I2, then okay. I1 is independent.
So it looks like it's a typo.
Cut and paste error. Another one. Sorry.
Happens.
Yeah, twice.
You call them crypto or something. Do you mean like that they're sort of opaquely equivalent systems? Is that what the word?
No, okay. When you have like, so the topological space is also defined in with multiple axioms, and they're equivalent, they're totally equivalent. Like, you can get from the circuit axioms to the independent set axioms and vice versa.
Mm-hmm. Great, okay, keep going.
So we can represent a graph by a matrix known as the incidence matrix. So I wanted to give you a, we don't work with an abstract set system like that. I mean, it doesn't have a whole lot of structure. So we want something that has maybe, it's larger than a graph, but maybe not so large that it has no structure. So that's why we focus on matroids representable over finite fields. I should say a certain cottage industry does. So we can represent a graph by a matrix known as the incidence matrix. And the way you construct the incidence matrix is you take E1, E2, E3, E4, E5, E6, those are the edges. And you line up the vertices over here, V1, V2, V3, V4, V5. And then E1 has vertices V1, V2, and that's why it's 1, 1, and so on. E2 has vertices V2, V3, and that's why it's 0, 1, 1, and so on. Now, if you do elementary row operations, that's, this is just R2, F2, the binary field, so there's no scalar multiple. But if you do R2 minus R1 and R3 minus R2, etc., you end up with, if you do a sequence of elementary row operations, so like you were doing Gaussian in F2, you end up with this matrix. So a graph theorist would think of a matrix like this, would think of a matrix representing the graph like this. And then there's a whole field called spectral graph theory that looks at the at eigenvalues, etc. A matroid theorist would look at a matrix like this. And this conveys some information that may be hidden over there. It conveys the fact that the size of the spanning tree is just 4. And that's why you have this sort of I4 over here, the 4 unit vectors, and that sort of an unnecessary row. So you could say it's a little bit more concise representation. And it doesn't necessarily have that appearance of the incidence matrix where it's just 2 ones per column, right? Because every edge has exactly 2 vertices that it's incident to. So it's just 2 ones per column. So a graph is a special kind of 0-1 matrix. Like not every 0-1 matrix that you throw out there has a graph representation. Some do, not all. In fact, there's a very nice algorithm by Tut where you can enter a 0-1 matrix, arbitrary 0-1 matrix, and it'll tell you if it's graphic or not. A binary matroid is any 0-1 matrix. So when we talk about matroids representable over F2, binary matroids, we're just talking about 0-1 matrices. And I could have put that right up there in the beginning as in, my talk is on 0-1 matrices. If you're talking about ternary matrices like 0-1, 2 over the finite field 0-1, 2, that's it. It's any 0-1, 2 matrix. So
I have 2 questions for you, Sandra.
Yes.
The first one is that row reduction, does it have graphical meaning? So my dissertation was in tropical geometry, and so there were certainly like degenerations of graphs, and so I can imagine degenerating your picture so that those 3 edges, E5, E1, and E2, all could sort of become one edge, and we'd still have sort of the same graph structurally, or at least topologically, but we'd have a different kind of information. Or if we collapsed V5 and V3, we'd end up with some like a loop. E6 would become a loop. Is there that kind of meaning to some of this?
Yes, there's a close connection between matroids and tropical geometry. And I can refer you to someone who knows it. Unfortunately, I don't know that. So Rhoda described matroids as having so many different, Weltanschauungen is, as he put it, different perspectives, that it is hard to believe that there's an object that encapsulates so much in it. So the answer to your question is yes, there is a close connection to it. I'm afraid I don't know much about tropical geometry. But if you figured it out, there might be a result that I could translate into matroids and we can get a paper out of it.
I'll think about it.
A collaboration is born. Right now.
The other question was, because of one of my colleagues studies something like this, I have students this year who've been walking around drawing these kinds of graphs, and rather than having like the number 1 associated with each edge, they have like a polynomial, and they're interpreting every like cycle as like a restriction on like, and that each vertex is somehow like has to have a balancing kind of condition where something about the matrix tells them how the polynomials associated with each edge have to combine. Is that sort of what happens when you move beyond F2, or is that like, and is that the same linearly dependent and independent thing that generated this from before, or is that a totally separate dimension?
That doesn't sound familiar to me.
Okay.
Something about what you said brings to mind balanced graphs, but I'm not sure that that's it. Yeah. So that doesn't sound familiar.
Great. And then we have one more question from the chat. Trevor asked if you could say a little bit more about Tut's theorem or Tut's algorithm.
Oh yeah. So it's in my Metroid software, OID. So many years ago, I put together with collaborators, one of whom is my husband, and some other people a package to work with matroids, which is why I could like spit out linearly independent subsets of columns as easily as I did. And one of the things we encoded was the Tutt's algorithm to determine if a 0-1 abstract, just a 0-1 matrix is a graph. So it's encoded, it's a click of a button and you can get your answer. It's a fantastic algorithm, it's polynomial time. And Tutt says that he was asked about it by an electrical engineering friend. And therefore he just sat down, thought about it and came up with this algorithm. It is fantastic. It really is. I can send you a link to all sorts of stuff about it. And, and if you're interested, I have software that will implement Tutt's algorithm.
Great, keep going, thank you.
Okay. So a binary matroid is any 0-1 matrix. So a graph with n vertices is a substructure of what we call the complete graph. Complete graph is a great name. For every pair of vertices, there is an edge, right? And took this straight from Wikipedia. So, when you study graphs from a structural point of view, you're studying substructures of these objects. Like this is the full thing that they sit in. So when I study binary matroids, well, I'm studying substructures of the projective geometry. So this is PG22. So if you have on rank 2, dimension 2, rank 3, this is the full structure. There's no more that you can put in over there if you're just looking at binary. This is PG32, the ternary plane. These are called the projective planes. And this is PG42 and so on. I'm sorry, this is the projective plane. This is rank 3, this is rank 4, etc. But they're all binary. So, and we can do the same for ternary and quaternary fields in any field of prime power. So the size of PGR minus 1, 2 is 2 to the R minus 1. So the thing about these structural results is graphs, the size of the complete graph is n choose 2, right? And R is the rank, which is the size of the spanning tree. So it's R plus 1 choose 2. Projective geometry, you're looking at an object that is exponential. It's exponentially large, and yet it behaves so similar to graphs. And that's the amazing thing. So it's very much larger object and still behaving very similar to graphs. So this is the Fano plane. So if you've done designs or something, this looks familiar. Combinatorial designs and maybe coding theory. So this is the Fano plane. This is actually the ternary plane. So this is PG23. And right at almost the same year as Hassler-Whitney published this paper, immediately Birkhoff and McLean, well-known algebraists, said, it's not just fields over fields and matrices, it's actually just, there are objects that are completely abstract that satisfy these matroid axioms. In fact, Birkhoff showed that a kind of lattice known as geometric lattice is a matroid. So, and there are examples of matroids that cannot be expressed by matrices. So it's a very, very broad definition. And many of us who work in this work in matrices over a finite field because it adds a little bit more structure to it. It's very much larger than graphs and still behaves very similar to graphs.
You okay?
So these are not graphs, these are geometries.
Shoes off.
So All right, so a few graph matroid concepts leading up to a small result. And just 4 more slides. So a minor of a graph. So we talked about subgraph before. It's a substructure of a graph defined in a certain way. And so the most generic way possible, you can remove some vertices, you can remove some edges. Minor is a little bit more specific. A minor is obtained by deleting edges. So you delete edges. For example, edge 1 over here, you can delete it. And contracting edges. So contracting is a new operation. And the easiest way to understand it is intuitive. You take an edge, right, and you squish it down to a point. So identify the 2 points, right, and that's it. That's contracting an edge, and it's a great name is you squish it down. So for example, if you have this edge 1 over here and you squish this down and identify these 2 vertices, then this is what you get. So a 5 kind of goes here, and then 10 over here, and you get this figure. So it's just as easy to do deletions and contractions in matrices. Deletion in a matrix, you just throw out the column. Contraction, you pivot on it, make sure that it's a unit vector, and then throw out the column and row. Contraction takes down the rank. So, so you lose a row and a column. Arguably, it's actually easier to do it in a matrix because it's just mechanical. So a graph is planar if it can be drawn so that its edges do not cross each other. Otherwise, it is non-planar. And, you know, this is a planar graph, even though it is drawn here with edges crossing, because you can sort of untangle it and draw it without edges crossing. And non-planar graphs, these are the smallest ones. If you just played around with it a little bit, you'll see that K5, the complete graph on 5 vertices, and this is denoted K33. It's called a bipartite graph. And they are the smallest non-planar graphs. And so a property is said to be closed under minors if when it holds for a graph, it also holds for all minors of the graph. For example, planarity. If a graph is planar, then all its minors are planar. Kuratowski in 1931, and then Wagner turned it into a minor result. Kuratowski had it in terms of subdivisions, proved that K5 and K33 are the main obstructions to planarity. So it was a landmark result in kind of started this field of excluded minor results. You have, you know, just these 2, and it's an if and only if characterization. So as long as your graph doesn't have this or this as a minor, then you're good, it's planar. And then in 1943, Dirac said, hey, wait a minute, it's actually really K33. K5 is not so important, it's just K33. And I have 3 connected over there. It's just that 3 connected, you need to remove at least 3 vertices to remove the graph, disconnect the graph. And a graph that is not 3 connected can be built up from its connected and 2 connected components. So in terms of structure theory, you know exactly how it behaves. So you look at 3 connected graphs. And I believe this is, yeah, the second last slide. This is my first published result. And, you know, I still like it very much. It indicates that it appears in textbooks now. Let M be a 3-connected binary matroid with an MK5 minor. Then it just behaves exactly like the graphs. And I sort of discovered this matroid that I named T12 that has a relationship to the Peterson graph, and it's just appear, you know, that in geometries, in a geometry, there are some objects that are definitely more important than others, like the Pappas geometry and the Desargues geometry and things like that. And in graphs too, there are some graphs that are more important than others. And in matroids, likewise, and like we saw K5 and K33, main obstruction to planarity. And I found another object like that. Every time people mention me, it comes up in other people's result. They put a reference to this paper. So, I mean, it's a small field and I've got a lot of references for this one paper. And yeah, that's it. That's just my result. And my final slide was a quote by Tut on what a matroid is. Sort of this, you take away the graph, you can even take away the matrix. These are like concrete objects, and then you get completely abstract. That's it. Nice. Thank you.
If you'd like to unmute the clap. Yay. So, Andrew, would you like to unmute and ask your question?
Yeah. I mean, so you point out that deletion and contraction, which are graph operations, make sense for a matrix. But I guess my question is, can you make sense of that for like a tensor? Like if I conceptualize a tensor and a basis as a like let's say a 3 tensor, right? So a cube of entries. Does anyone know? Is there any extension of deletion or contraction? I mean, deletion, I guess, is clear.
I want to answer yes. I think the answer would be yes. Anytime you have a basis, you're really looking at a matroid-like object. So I want to answer yes. I just don't know the details.
Someone's kids are having
fun. Thank you.
I have 2 questions, and I'm not sure which one to ask. So can everybody hear me? Am I?
Yeah, I can hear.
Oh, okay. So you said that every graph on 0 and 1 is a binary matroid, and graphs are a special case of those?
Yes, every 0-1 matrix is basically a binary matroid.
Okay, so my question was, if you change the 2 to any prime in your finite field, you still have matroids, right?
Mm-hmm.
What do graphs turn into? Does that question even make sense?
A graph is representable over every field. So there will be a matrix over any field that represents the graph.
Okay.
Yeah.
So
that's a good question, actually. That's a deep question. Yeah.
The question I was asking before was essentially a conjecture related to what Douglas is saying there. It was like, if you have more than 2, does the higher numbers represent, say, like colorings on the graph or something like that? So you have to like label with that extra information, or is it just the graph? Is that, Douglas, is that a fair version of your question?
Yeah, and actually I tried to pop in when you asked that question, and I wasn't unmuted. So.
Okay. Okay, it's just the graph. Yeah. Okay. So a graph, there will be a matrix over any finite field that will represent that graph. Yeah. So you can think of graphs as a sort of, like a set, and then around it binary matroids, and then ternary matroids. Of course, it's not around that. It's like it intersects it. But graphs is right in the middle of all the finite fields, matrices over finite fields. And then matroids are much more general objects. So.
Thank you.
You're welcome. Yeah, they were both. That was a good question, but I didn't understand it when you asked, Brian. But that's a good question. Yeah.
Well, I didn't understand what I was asking. So. Douglas, you had another question? I don't see anything else in the chat right now.
Okay, sure. And again, it's one that I'm not sure is even well posed. But so, sorry, I'm scrolling through my notes. You had that a graph is a substructure of the connected graph, and the connected graph has size n choose 2.
Complete graph.
Complete graph, yeah.
Yeah. Mm-hmm.
Okay, and then you had that your binary matroids are substructures of the Rankar binary projective geometry, which has size 2 to the r minus 1.
Yes.
Okay, so I know that if you add up all the n choose 2's, you get 2 to the n. So is there any sort of additive relationship between the complete graphs and the binary projective geometry?
I was kind of wondering something along that line too, because I mean, I don't know anything about projective geometry, but I was
Me neither.
noticing that the things that you had for the examples of the different projective geometries were all of the different combinations that had at least one. And so it was all of the different possibilities of ones and zeros in each spot, other than the case that had only zeros.
Mm-hmm. That's the 2 to the r minus 1. Yeah.
Yeah.
So for a fixed n, the largest object is n choose 2. And if you want to talk in ranks, then n is equal to r plus 1. So it's r plus 1 choose 2. For a fixed r, the largest object for binary matroid has size 2 to the r minus 1. And you're saying that if you add up all the complete graphs, then you get like 2 to the n, right? So
but Rob points out that n choose k's add up to a 2 to the something rather than n choose 2's. Douglas, was that a typo?
That was I guess a braino, yeah. That was thank you.
okay, thank you, Rob, for answering that for me.
Yeah, that was yeah, thank you.
Steven, did you want to say something? I know that you put your digital hand up.
I did put my hand up. So
it was Andrew who caught it, not Rob. Rob has another question later. Go ahead, Steven.
Okay, yeah. So I was really excited for this talk to learn about matroids because they remind me of my greatest failure in mathematics outreach.
Say again, I didn't catch that.
So matroids are related to my biggest failure in mathematics outreach because I run an organization that does math puzzle scavenger hunts, and we had a science fiction theme one year, and there's a video game called Metroid. And so we really wanted a Metroid-themed Metroid's puzzle. But the problem we ran into is, how does one create, this is for like high school students, how do you create a Metroid puzzle that isn't really just graph theory or combinatorial design theory? Or we struggled to come up with a compelling scenario for the kids about matroids that wasn't really just one of those other things, because it does such a good job of abstracting all these other things. I'm trying to think of us, I don't know if, yeah, what sort of scenario, if you were to describe a matroid to a high school student, do you have sort of an elevator pitch for what that is without?
So if I had to describe a matroid to a high school student, I would describe a graph. Because so a matroid is a perspective on all these objects. So it's a perspective on graphs, it's a perspective on combinatorial designs, and it's a perspective on projective geometries, all of which are also studied as fields of their own. So it's sometimes when you look at it from a higher abstraction, you can prove some of the results easier than if you were just sort of working within the field itself. And so my elevator pitch to a student would be, you know, mathematical objects are not as different as they seem when you first look at them. So you can study all these objects separately, and then you can observe that, well, you're really studying something that is very similar if you look at it from an abstraction point of view. But I usually, when I do undergraduate research projects, I sort of stay with graphs, because a matroid requires like some understanding of finite fields, and you don't always get undergraduate majors. By the time they've done finite fields and stuff, they're ready to graduate. Yeah, so it's a little bit hard to kind of bring it down to sort of like a high school level or even an undergraduate level, other than there is this abstraction on top of all the other objects that you study independently of each other that maybe ties everything together. And it's good, but maybe, I don't know, it's powerful and good and all those good things, but I don't know, sometimes you end up still down here looking at the details, right? So it's a perspective on things.
So Sandra, that connects to the last question we have in the chat. On your second to last slide, you mentioned dual. I know what a dual graph is. Can you say a little bit more about what you meant by dual in that context?
Yes, so planar graphs have duals, right? Like you can put vertices on the planes and connect two planes that have a common edge. But a non-planar graph, it doesn't have a geometric dual. But if you think of that planar graph as a matrix, then the matrix has a dual. It's if you have IRD as the matrix, D is the right-hand side. Over here, for example, I'll just scroll up and show you where did we have our matrix. Yeah, so if you have I4 and this is D, then minus D transpose IN minus R is the dual. So you can construct the dual of a non-planar graph from a matroid point of view, even though you can't picture it. So every matroid has a dual matroid. If you define matroid in terms of the basis axiom, which I didn't do, I did two, but I didn't do the basis axiom, then if B is a basis, E minus B is also a basis. So matroids come in pairs. And so that's the dual that I mentioned, as in you sort of exclude K5, where are we? Yeah, if you then it has a minor isomorphic to K33 or its dual, K33, the abstract dual, because K33 is not planar. Mm-hmm. That's a good question, yeah.
So since you're doing it with matrices, right, and there's a transpose in there, is that, I mean, is there a way to understand, is that like coming from like an inner product dual, like a metric dual? Is that, I mean, is there a way to understand the standard inner product as having content?
Yeah, it's the orthogonal dual. Yeah, it's the same thing. So here, for example, in T12, this is self-dual. So if you do the transpose here, it's the same as the original matroid. Yes, it's the same thing. It's orthogonality. So some people call it orthogonal dual.
So what is, I mean, is there a, like if you have a graph, right? Is there a graph theoretic interpretation of orthogonality?
Yes, for planar graphs, right? So for a planar graph, the geometric dual is where you have, where you can put a vertex in every plane and join two vertices by an edge if the planes share a common boundary. So you can actually draw out the duals for planar graphs. But for non-planar graphs where you have crossing edges, that won't work. So, so the answer to your question is that's the orthogonality visual for planar graphs. It's not there for non-planar graphs, but it exists as a matrix.
So we're at our time. I want to make sure that if people want to slip away, it's okay. Just to do our brief, let's see, I think I can do this. Yeah, so just a brief thing just to share my screen. So our next talk next week is actually me. I'm going to be talking about how do mathematicians believe. I'm going to talk about the sort of philosophy, sociology, psychology of mathematics. I might say a couple of provocative things about how mathematicians believe. And so I hope many of you will join us. So can we unmute one more time and thank Sandra?
Thank you.
Thanks, Sandra. This is great.
Thank you for being such a forgiving audience.
We're friends, right?
Yeah.